Hi class, we are now on 6.5a. This is going to be broken down into 3 different sections. So we're on A. So in earlier lessons, we described the behavior of different types of compounds when dissolved in water. Recall that when an ionic compound dissolves in water, think of something like sodium chloride, it dissociates into cations and anions. And the water molecules surround the ions so much, it's called hydration. So here's a perfect example of it completely. That is an attraction stronger than the ions coming back together. That is, the ions that make up the compound are pulled apart and are surrounded by water molecules. That's called hydration. This behavior enables different ions to react in different ways. And here I found a nice little GIF that kind of gives an idea of what's happening. When describing the chemical process that takes place in solution, we use 2 different equation styles. In a molecular equation, we write ions together as compounds. For example, we can write the equation showing how potassium bromide dissolves. So we start with potassium bromide, that's a solid, and it then goes into potassium bromide in aqueous solution. So it's been dissolved into ions. So that would look similar to what you see here. In the molecular equation, the only difference is the phase symbol of solid and aqueous. In an ionic equation, we show the dissociated ions as separate species. Using an ionic equation, we show potassium bromide as a solid that dissolves into potassium ions and bromide ions. And what you see here is you see the potassium, and then you see, and bromide, and then it's in ions in aqueous and ions in aqueous. So what that means is it looks now like this. They are separate, so that's why you see them as separate. But we can also write it at this, and this means the same thing as this. But be careful, if it's asking for molecular means you leave it intact. And if it's ionic, then if anything is an ionic, not this is a solid. If it's a solid, you do not write it that way. But anything that can be in ionic form has to be in ionic form. This is a page from another one of my slides. This is also just repeating the same thing, but with a different equation, so you can see. A molecular equation showing the complete neutral formulas. So you see there's silver nitrate in aqueous solution and sodium chloride in aqueous solution. But when these are placed together, they produce silver chloride, that is a solid, and sodium nitrate. These are ions just swimming in the aqueous solution. They did not interact with each other. Now, when it's asked for complete ionic equations, which is what we're building up to, this shows an ion form. So basically, you break everything up. So you take a line and you break it up and you put the charges with it appropriately and how many. So in this case, we see silver as an ion, nitrate as an ion, salt as an ion. Sorry, this should be up. That's why it looks weird. And then on this side, this is complete ionic. We see that we have silver chloride as a solid, which we leave, and then anything else is ions. So we need to make you need to understand the definition of what is molecular and what that involves, and ionic. And the word ionic is in there, but is it complete ionic? We're going to go into there's another type of ionic, which is net ionic, and I'll cover that later. Okay, so writing ionic equations, here's the practice. So we're going to look at this one. This is magnesium nitrate as a solid, and then it dissolves in water. And when it dissolves in water, it is now magnesium nitrate in aqueous solution. So when we look at that, when we look at this molecular equation, we simply change the phase symbol from solid to aqueous because we know that this compound has dissolved. So it is still the same compound, it's just dissolved now in water. And when it's water, it's something in water, it's an aqueous solution. So we write this in an ionic equation. So we now have to separate the ions. So if it's a solid, we do not touch it, we leave that alone. But we have to break this up. So you kind of try to have to do a line and to separate them. So we take the magnesium, and you can see that it's got a magnesium ion. So remember, we uncrisscross these is what you want to do. So here's magnesium with the 2+ charge. But we have to account for the fact that there's 2 of these. So simply you just add the 2 in front to account for the 2 nitrate ions that need to be involved in this. So by looking at this, we can see that this dissolved into magnesium ions, and for every 1 magnesium ion, we need 2 nitrate ions in aqueous solution. But remember, even though this is an ionic compound, If it's a solid, we don't mess with it. We leave that alone. Okay, so predicting solubility. Solubility is when something dissolves in water. And think of salt in water. You can add salt to water and stir it, and it goes in, and you cannot tell that there's salt in water by looking at it until, of course, you get to a certain point, and we will eventually cover that as well. It becomes saturated. But if you keep at, for a while, let's just pretend you add a teaspoon of salt to a pitcher of water. It's going to dissolve. You do not see that there's something in there. However, there are some ionic compounds that do not dissolve. And what is the meaning of insoluble? Insoluble means it did not dissolve. You start getting a white film. It could be thick like this. It could be foggy, but not. When we talk about insoluble, we think it's just not going into water. So when we look at that, insoluble means it can become this, this word is precipitate. It's insoluble, or it can look like this. Both of these are insoluble. There's just different degrees of how, if you want to think of it like thickness of what you're looking at. So now we're going to look at what determines whether a compound is water soluble. So predicting water solubility. I lost my place. To answer this question, let's think about the energy changes that occur when an ionic solid disassociates in water. In an ionic lattice, that's when it's very patterned, it's patterned together, very structured pattern. Let me put it that way. That's an ionic lattice. Ions are stabilized by the oppositely charged ions that surround them. So that attraction holds them together very, very, or in an organized manner. When they disassociate, the ions are stabilized by the water molecules. Which situation is more energetically favorable? So basically, in chemistry, everything is about the lowest energy. That makes it the most stable. So if a compound is more energetically favorable to dissolve, it will dissolve. If it's more energetically favorable to stay together, it will stay together and not dissolve. So the answer to this question determines whether a compound will dissolve. Okay, so the solubility of ionic compounds depends on the charge of the ions, the size of the ions, and the way the ions are packed together. The more strongly the ions bind to each other, the less likely they are to dissolve in water. As a general rule, the greater the charge of an ion, the more tightly it sticks to oppositely charged ions, which means it's just a greater pull. For example, most compounds composed of ions with a +1 charge or a negative charge, such as sodium chloride, potassium nitrate, so you can see here sodium chloride, potassium nitrate, ammonium bromide, are soluble in water because they all have a +1 or a -1 charge. But compounds composed of ions with charges of 2 or 3 tend to be insoluble. Iron 3 oxide, lead 2 sulfide, let me see, iron 3 oxide, lead 2 sulfide. Remember, these are reduced down. That's why you don't see it. It's a 2 and a 2. See, perfect example right here. Should have looked there. I wasn't looking there. Yes, even I don't always notice, and I put these slides together. And barium carbonate, again, another one with a 2 and a 2, are all insoluble in water. There are a few important exceptions to the rule. The way ions fit together can be hard to predict, and sometimes ionic compounds exhibit surprisingly stability. For example, ionic compounds containing halogen ions, fluoride, chloride, bromide, and iodide, are nearly always water soluble, unless they are bonded to silver or lead. Following this rule, potassium fluoride, zinc chloride, iron 2 bromide, and copper iodide are all soluble. On the other hand, silver fluoride, silver chloride, lead 2 bromide, and lead 2 iodide are all insoluble. So this is an interesting thing where you see some that are and some that aren't. Now, remember I told you guys to print out that handy I call it a cheat sheet. There is a solubility table in there, and I'm going to show you how to use it. So let's go on. So the solubilities of common ionic compounds are summarized in the table. Note some of the key trends. Compounds containing alkali metals are nearly always soluble. By the way, if you look at the table in your printout, it's going to look a little different than this. If you do a search of solubility rules on the internet, you will find all sorts of different type of tables. They all have the same information, but they're all looking very different. I don't know why. Compounds containing the ammonium ion. Okay, so if we look here, we have alkali metals, and you can see that, first let me break this down because students have a hard time understanding a table. And if you look at all the different tables, they make it as complicated as possible in some. Okay, so this is compounds containing these ions are nearly always soluble. What does that mean? That means that any compound that has these is soluble in water. I don't like that they put nearly, but let's just pretend it says always because it's easier to understand. Because what does nearly mean? That doesn't give me really anything to work with. So if you have a compound that is, for instance, with lithium, sodium, potassium, or rubidium, that means that it's going to dissolve in aqueous solution. Compounds containing these ions are usually soluble. What does that mean? That means that if you have these compounds attached to whatever cations, they will be soluble, except these two. Anything that's attached to these two halides, with halides, meaning any of these that are attached, will not be. Sulfate are usually soluble, except when it's attached to these. If it's not attached to these, it's soluble and not soluble. Most other ions. I do not like this table. I just think it could have been done better, but this is what they gave us to work with. So let me start at the beginning. Alkali metals are nearly always soluble. Compounds containing ammonium are always soluble. Here's ammonium. It's just going to go down. Compounds containing the large oxyanions nitrate, chlorate, perchlorate, and acetate are always soluble. Compounds containing sulfate are usually soluble, but there's an exception when it's bonded to barium, calcium, lead, and silver. And most other, did I skip over the halides? Compounds containing halides, fluoride, chloride, bromide, and iodide are soluble except when bonded to silver or lead. And then most other compounds are insoluble. These guidelines provide a useful approximation for determining whether or not compounds are water soluble. However, many compounds are slightly soluble, meaning they have a very small number of ions that will dissolve, but most of the ionic solid will not. In some applications, you may need to know the solubilities more precisely, geez, than is given here. Solubility also depends on temperature. Many ionic compounds that are insoluble at room temperature become quite soluble at higher temperatures. So we're also going to cover that eventually. A good example of, I didn't like tea growing up, but I think if you can increase the amount of sugar that's dissolved in tea when it's hot, and then it comes out when it's cold. I don't know. I was never a big tea fan growing up, but I used to know something slightly like that. I'm sure somebody can tell me. Okay, so here is another solubility table. This one's weird because, yes, it does make sense, but I've never seen it given out in a class before. You can find this actually online, something like this. So how do you read this? Well, if it's yellow, it's soluble. If it's blue, it's insoluble. And whatever you have, you look for those compounds. So here we have calcium chloride. So we got to look for calcium, and these are all cations, so we can start at the top. So here's calcium, and anything related with calcium as a cation, you will see how it's affected. So calcium chloride, we have chloride, and it's a yellow. So this is soluble. Now we have to go to magnesium hydroxide. So here's magnesium, and we find hydroxide right here, and it's blue, so it's insoluble. I'm going to tell you right now, I've never seen a class being given this, even though they exist. So this is the first time I've seen it. It is easy to read, but there's a lot of, how do I say this? Sometimes having a chart that's similar to this is a lot easier, even though you think that this is easier to use, because this I don't know how to explain it. It's not going to make sense. But anyways, this is a good chart to have, but I just don't see it normally passed out. Okay, so let's look at some other solubility examples. So determine whether the following compounds are soluble or not. So how do you read this? Okay, so we have sodium phosphate. If either of these are on here, it's going to tell you what's happening. So let's see, we have sodium. So here is sodium. So because it says these are nearly always soluble, because it's got sodium as a cation, it's soluble. We don't even have to worry about phosphate unless there was an exception to it. But it's saying that these are always soluble on the top ones. Here we have aluminum chloride. Okay, so it's nothing here. So we have to go down to that. We have halides. So we have a halide because we have chloride. Here's the exceptions, and aluminum's not part of it, so this is soluble. Now we have calcium carbonate. So we don't have anything here. We don't have anything here, so we have to go down to the bottom ones, right? And let's see, we have calcium. Why isn't, okay, this one's not telling. Oh, basically, this is why I don't like this table. Carbonate's not on here, and calcium's not on here. So what it's saying is because it's not on here, it's insoluble. So it applies to this one. I don't like that. I would rather have something that tells more. Let's see if it's on here. I'm just going to wing this and see if it's here. We have calcium and we have carbonate, and it is blue, so it's insoluble. I don't like this table. Okay, so determine whether the following are soluble or insoluble in water. So we have iron 3 chloride. Do I have them all? Yeah, I do. Okay, so let's just go through. I'm going to show you the answers so we can help you understand how to read it. Because like I told you, some of these are, again, here's this table that I don't like. Okay, so let's take a look. We have chloride and we have exceptions. And this is not exceptions. Iron is not, so it's soluble. We have calcium hydroxide. Do we see anything with hydroxide or calcium? Nothing that's related, so it's insoluble. We have sodium phosphate. That's not right because sodium is always, let's see if it's on here, by the way. Let's see if we can find it. It doesn't have sodium, but it has phosphate. Oh, here it is. Look at sodium phosphate is soluble. So this is an error that I didn't catch. So, and it's funny because we just used it on this one as soluble. So it's showing here it's soluble, and now it's showing it's insoluble. So this is wrong. Write this off. This is wrong because it's showing right here. And you can always check that other slide. Okay, so we have now ammonium carbonate. It's a good thing I'm going through this. Ammonium is right here, so it's attached. We don't even have to worry about carbonate. It's soluble. Now we have barium carbonate. So barium carbonate is not listed here, so it's going to be insoluble. And we have silver chloride. Well, we have halides, and there's an exception right now. That means it's a solid, so it's insoluble. All right, this is a table. This is from my other slides. This is a table that seems more confusing, but I actually like it because it confirms, instead of just saying it's another ion, we can confirm whether it's a solid or not. It's not soluble. So don't pay attention to this. This is from another class. But let me explain how this works. So again, any of these, this is saying that are mostly soluble. So if there's any exceptions, that's none. That means that if there's anything attached to these, it dissolves. Anything attached to these, it dissolves. Anything attached to these, there are exceptions. When these are paired with silver, mercury, or lead, the compound is insoluble. But if it's not, then it's fine. Sulfate. If it's attached to calcium, strontium, barium, or lead, it's insoluble. But anything that's not is soluble. Now, let's look at this bottom part. Compounds containing these are mostly insoluble. So if they are attached, they are going to not dissolve. So if you have anything attached to hydroxide or sulfide, it is insoluble, except for, now that means these will dissolve. Where these mean they don't dissolve, these means they will. When either of these ions are paired with any of these above, it's soluble, which already matches this. When sulfide pairs with calcium, strontium, or barium, the compound is soluble. So, which is, it's interesting because see, sulfate is not, but sulfide is soluble with any of these same ones. When hydroxide pairs with calcium, strontium, or barium, the compound is slightly soluble, but for most cases, they consider it just, it doesn't dissolve. And here we have carbonate and phosphate, which we couldn't show on the other one. It just gave that standard that if it's not up here, it's insoluble. But this kind of helps you confirm. When it's paired with any of these above, it's soluble. And if it's paired with anything else, it's not. So hopefully that makes sense to you guys. Okay, I actually broke these up. Okay, so let's take a look at silver bromide. So silver bromide, we have halides here, and there is silver as an exception. So if it's an exception, it's going to be insoluble. Now we have calcium chloride. So let's look here. We don't have calcium here, so this is soluble. We have lead nitrate. I'm going to tell you right now, there are certain ones it's just easy to memorize because it saves you a headache. If you look, there's lithium, sodium. These are group 1s. They are easy to understand that they're anything attached to them. Another one that's easy to understand is nitrate. Nitrates, anything attached to nitrates or acetates, they're soluble. So the minute I see nitrate, I know it's soluble. Oh, I cheated on this one and gave you guys. Okay, so sulfate, if it's paired with lead, and it is,